let's look at Kirchhoff's law, and there are two laws here, and the first law is called the Kirchhoff current law, or in short KCL, as well as the Kirchhoff voltage law, KVL. There are fundamental properties of circuit that make analysis possible. So let me just explain very briefly what KCL is. KCL states very simply that the sum of all current entering a node is equal to 0. Another way to put it is that what goes in must come out, and therefore the sum of the currents entering a node is equal to the sum of the current leaving a node, the same node. KVL states something which is, say, the sum of the voltages around any loop in a circuit is equal to 0. So if you go around in the loop, starting from one place and ending back in the same place, and you count all the ups and downs in the voltages, adding all these ups and downs together, when you return back to the same place, you have a sum of 0. So these are the two very basic laws, and I would like to ask the question that are these laws, what are these laws based on? Are they physical laws, or they are just definitions, or they're experimental laws? Very similar to what we asked about the nature of Ohm's law, V equal to IR. Now, the idea that you can think about a node whereby multiple wires enter into as being similar to the intersection of a roadway, and the number of cars entering the intersection is equal to the number of cars leaving the intersection, or else cars will accumulate at that intersection. So, physically speaking, KCL, Kirchhoff current law, is a statement of the conservation of charges. What goes in must come out. But if in case a node comprises something very much like a Van de Graaff generator, whereby electrons are moved up to the sphere of the Van de Graaff generator, Kirchhoff current law may not hold because there's accumulation of electron on the sphere on top of the Van de Graaff generator. So here we are making the assumption that the element does not store up electron, and this to a large degree is true in circuits. But this is not something that is inviolable. It can be violated if in case the node ended up piling up cars without leaving the node. But in almost all the case in circuit, that KCL is true because what goes in must eventually goes out. Now, the second, we can look at it mathematically, and what we can do is that if you have current, and very often it would be very convenient to look at current as being positive when it enters the node, which means that if it leaves the node, the actual value of the current is negative. Now, mathematically what it says is that the sum of the current entering the node is equal to 0. You need not worry actually whether the current is flowing this way or the other way, but you define the direction in this way so that on this wire 1 at time t would be positive if really there is a flow of positive charges into the node. So what you have is very similar, is the summing over J of all the wire J's from 1 to n of the current on the wire J has to be equal to 0 at every point in time. So that's a mathematical statement of the Kirchhoff current law. And let me give you an example of the Christmas light, whereby you may have a string of Christmas light and you connect it to 120 volt power source on this side, and then you have all these 50 of the 1 watt light bulbs in parallel. So the current coming down here is I of S. S stands for the sum of the current, and it will be equally divided into the 50 light bulbs in this string of Christmas light, and therefore you can say if each of the current through the light bulbs is equal to I, then 50 I would be equal to IS. So what goes in must equal to what comes out of the 50 light bulbs. We define I in the same direction. What goes in IS equal to sum of 50 of the I. And therefore you can say that I is 1/50th of the current that's provided by the source. So you can do that as a result of KCL simply. To solve for IS, one way to say is that the I through each of the light bulb B is equal to 1 watt divided by 120 volt, and that's simply P equal to IB. And therefore each of that is 8.3 milliampere. And if you apply KCL to the top node, what goes in is IS, and what goes out is 50 IB, and the minus simply is because the current IB is leaving the node, and that's equal to 0. You solve for IS, and you get an IS equal to 50 IB equal to 417 of milliampere. Now, let's move on to talk about KVL, Kirchhoff voltage law. And applying KVL is analogous to taking a walk while paying attention to the increases and decreases in altitude. So if you walk around in a loop, you end your walk where you started, the net change in altitude is 0. And it's true on any path that you take for your walk. Now the question is, why is that true? And we can understand this is true for hiking. If you start and end on the same place, then there's some amount of work that you do. It's equal to 0 because some places you're going uphill, you're doing work, and you're coming downhill. Actually, work is released in the process. So it has to do with conservation of energy, that in a closed loop, the amount of energy put into the system or taken out of the system is equal to 0. And instead of talking about gravitational potential, we're talking about voltage potential here. So as a result of the conservation of energy. So in this case here, the same case with the 50 light 50 light bulbs here. So you can choose any of the loop. Now let me just explain. The sum of voltages across these things is equal to 0. Really, it doesn't have to be an actual loop. Like I can go through here and then go, and then what you have is that in this case here, the sum of the voltages around the loop would be equal to 0. I can choose another loop, and one very crazy looking loop would be going here, and then I can straight down from this to here, even though there's no circuit in between. But that's perfectly legitimate because I can always just say talk about the voltage difference between this point and this point. So let's look at what you have here. Is that this is important. A loop is any closed path through a circuit in which no node is encountered more than once. That's the definition of loop, because you can go from A to B to C, back to A, and then if you go to E and back to A, that would be visiting the node A twice. That's not considered a loop. Now, a voltage encounter from positive to negative is positive, and the voltage encounter from negative to positive is negative. And then I could draw this very simply. For example, I have a node. For example, I have a power source here, and let's say this is 5 volt, and I may have a resistor here. So what you have here is that if I consider the loop, and you always can draw the loop, the convention very often is that you draw the loop in a clockwise direction, but it's really immaterial whether it's clockwise or anti-clockwise. So if you do the loop here, defining the direction, the first thing you enter is the voltage. So if you say this is 5 volt, because you enter the negative node, you put the minus sign there, right there. Let me just use black color. Minus, because of you're entering the minus sign here, minus 5 volt, plus, if I call it VR, plus V out is equal to 0, and therefore V out is equal to 5 volt. Now the question is, do you need to put a plus or minus sign across a resistor? Well, you could have put there like that, but very often you would define the, it would be good to put the plus or minus sign there so that the V out actually is defined according to this. And therefore, because you're entering the positive terminal, you would have it a positive sign here. And that, when you return back the same place, same node, is equal to 0. Now, very often we just don't do that and just assume that whenever you have a current flowing into a resistor, it's positive. So, example, the voltage here, and we're doing the loop, which is this loop here. And what you have is that because I'm entering the minus terminal is minus V1, and I have a positive here, plus V2, and a plus V3 would be equal to 0. So that would be an example of how you account for the voltage increase and decrease around a loop. So what will happen if you forget or deliberately ignore the convention of plus and minus is positive and went around in a loop using minus to positive, using minus to, then you would mess up. You would get the number incorrect. So when you have a loop and when you enter the negative terminal of that loop defined by the plus and minus sign is negative. Otherwise, you will have an incorrect accounting of the increase and the drop of the voltages. Christmas light. This is the wrong way to build Christmas lights because you're putting the voltages in series. The reason why it's a wrong way is if any one of the light bulb is burned, then you have an open circuit and therefore the other 49 light bulbs will not work. But if you had what we did earlier, putting them in parallel, then one light bulb got open circuit, the other light bulb is still okay. To solve for VB, which in this case here is the voltage across this one here, what you do is then you have minus 120 volt plus VB, all the way 50 times of plus VB go back to the same node and therefore it's equal to 0. So what you have is that 50 VB minus 120 volt is equal to 0 and therefore VB is equal to 2.4 volt. So it is a voltage divider that divides up the voltages across the entire loop 50 times. Sometimes you may want to model thermal noise of a voltage source as an additional resistor. So R is a resistor in which the charged particle vibrate due to random thermal motion, because this could very well be a transistor, and because the electron move inside this temperature, and therefore there's a resistance. Instead of modeling this as a pure voltage source, you put a resistance outside of the source. So what you have sometimes also, you have not only the voltage, there's resistance inside the source, but also you have a noise of the voltage, and therefore you can put two of the voltage, one which is the desirable voltage, the other is a random noise source, and then you can put two in tandem. So more on the model, RS is called an ideal resistor, one in which there is no noise, and VN represents thermal noise in creating a voltage noise, sometimes in the amplifier, in the amplifier itself. So the equivalent voltage would be the total is the sum of the ideal voltage as well as the noise voltage. So you can solve for the V total using the KVL, and therefore KVL and KCL together would be useful for calculating voltages and current. And there will be an exercise that you have to go through in this class so that you would know whether you've learned the material.